Welcome to the Ontario High School Chemistry video podcast regarding how to do percent composition, determination of empirical molecular formula problems. Let's start with percent composition problems. We're going to determine the percent composition of each element in iron 2 phosphate, which is Fe3PO4 in parentheses 2. So in order to do these, first we want to find the molar mass. So there are 3 irons, so we have 3 multiplied by 55.847 grams per mole of iron. That's found on the periodic table, which gives us 167.54 grams of iron in the compound. There are 2 phosphorus atoms, or 2 moles of phosphorus atoms for every mole of iron 2 phosphate. So 2 times 31 grams per mole gives us 62 grams of phosphorus. And finally, there are 8 oxygens, and you'll notice that we get 8 by taking the subscript for oxygen, which is 4, times the subscript outside the parentheses to get a total of 8. We multiply that by the 16 grams per mole for oxygen, and we get that there are 128 grams of oxygen in a mole of this compound. When we add this together, we get a total molar mass of 357.54 grams per mole. And it's really convenient to calculate the molar mass this way when finding percent composition, because I have the mass of each individual element in addition to the mass of the entire compound, and that's going to make this problem a lot easier to solve. Once we have the molar mass and the mass of each element in the compound, we're going to use a basic equation of this, the percent of any element X. The mass of X in a compound divided by the total mass of the compound times 100 will give us the percent mass of that element. So let's start with iron. The percent iron would be equal to the mass of iron in the compound, which is 167.54 grams of iron, divided by the molar mass, 357.54 grams of iron 2 phosphate, iron 2 phosphate, and then we'll multiply that times 100 to get 46.9%. So the percent iron in the compound is 46.9% by mass. Moving on to the other 2 elements that we're interested in, the percent phosphorus would be equal to the 62 grams of phosphorus divided by the molar mass of iron 2 phosphate, which is 357.54 grams. And then we multiply that by 100 to get 17.3% phosphorus in the compound by mass. And for the percent oxygen, the 128 grams of oxygen in the compound divided by the molar mass, 357.54 grams of iron 2 phosphate, times 100 gives us 35.8% oxygen in the compound. Well, here's a summary of what we've done so far, and you can see we do have our 46.9% iron, 17.3% phosphorus, and 35.8% oxygen, making up the iron 2 phosphate compound. When you go to check your work on this, add the percentages up and make sure that they add to 100%, and it's a quick way to make sure that you haven't made any mistakes in that. Well, now that we've mastered percent composition, we want to look at empirical and molecular formulas. The definition of an empirical formula is simply that it is the simplest whole number ratio of atoms of different elements in a compound. The empirical formula may or may not be the same as the molecular formula, but the empirical formula for ionic compounds is always the same as the formula for the compound. So if you have an ionic compound that you're examining, when you determine the empirical formula, that will be its formula. If it's a compound, covalent compound or molecular compound that does not contain a metal, where the electrons are shared between the atoms, then oftentimes the molecular formula will be different than the empirical formula. So we want to be able to determine both. There's a poem available that can help you with a system of solving for empirical and molecular formulas. So this poem should be memorized, and it's simply this: percent to mass, mass to mole, divide by small, multiply to whole. Oftentimes when you're solving for an empirical formula, they will give you a percentage of the elements that are in the compound, and since the percentage is part of 100, what we do is we just assume that we have 100 grams of the compound, and we just make the percentage grams. So if something is 10%, we would make that 10 grams. So that's what the percent to mass is. Once we have mass, we then change that to moles, doing the mole conversions that we learned in the last podcast. Once all of the elements in the compound have been converted to moles, we then find the mole ratio by dividing by the smallest mole quantity, having each mole quantity divided by the smallest. If all of those are whole numbers, at that point you can write your empirical formula, but sometimes you'll have a mole ratio of say 2.5 to 1 or 1.67 to 1, and in a case like that you'll need to multiply all of the mole values in the empirical formula by a number that converts the one that is a fraction to a whole number, and you'll see that as we go on here. So here's a sample problem for us to apply the poem to as we go to solve this. Determine the empirical and molecular formulas for butane, which contains 82.8% carbon and 17.2% hydrogen by mass. The molar mass of the butane is 58 grams per mole. So my first step is to take percent to mass. My 82.8% carbon becomes 82.8 grams of carbon. My 17.2% hydrogen becomes 17.2 grams of hydrogen. After converting our percent to mass, we then take the mass and convert to moles. So we take our 82.8 grams of carbon times the conversion factor of 1 mole of carbon for every 12 grams of carbon. That gives us 6.90 moles of carbon. Our 17.2 grams of hydrogen times 1 mole of hydrogen over 1 gram of hydrogen is equal to 17.2 moles of hydrogen. If converting to moles is problematic for you, there is a video podcast called Moles and Mole Conversions that deals with this specifically. You may want to go back and review that. Once we've found the moles, then we're going to do the step divide by small. In this, we're going to find the mole ratio by dividing all the mole quantities by the smallest. The smallest has to do with carbon, so 6.90 divided by 6.90 gives us 1 mole of carbon. The hydrogen is 17.2 divided by 6.90, which gives us 2.5 moles of hydrogen. As we examine the mole ratio, we find that we have 2.5 moles of hydrogen for every carbon. If we were to write an empirical formula from this mole ratio, it would be CH2.5. And one of the things that we know is that we cannot have a part of an atom in a molecule. And so this is where the last step comes into play. We need to multiply to a whole. So if the mole ratio is not a whole number, we're going to multiply all the mole ratios by the smallest whole number that will make them whole. In this case, it would be 2. So again, we have a mole ratio before multiplying to a whole of 1 to 2.5. We multiply by 2, and essentially what we do is just put the empirical formula into parentheses and then multiply by a coefficient of 2. And so the coefficient of 2 times the subscripts in the formula would give us C2H5. So the empirical formula for this is C2H5. This is the end of part 1 of the video podcast series here at Ontario High School that deals with empirical molecular formulas and percent composition. I want to leave you with a quote from Kelsey Grammer. I think it's your duty to overcome what you inherit in life. Stay tuned for part 2. I wish you well.